Swayam Prabha. Digital India. Educated India.
Good morning and welcome to this the fourth lecture of the course Stochastic Hydrology. If you recall, what we have done in the last class, that is lecture number 3, is that we introduced the concept of independent random variables. Recall that we said two random variables are independent if and only if the joint density function f of x comma y is given by the product of the marginal density functions g of x into h of y. Then we considered functions of random variables. So, initially we introduced functions of a single random variable. Let us say y is equal to h of x is a function of a single random variable x. Then we introduced how to compute how to estimate the PDF of y given the PDF of x. Then we went on to consider functions of two random variables given f of x comma y, that is a joint density function of x and y, how to compute the joint density of u comma v, where u and v are functions of x and y. They are continuous functions and we have seen the examples for continuous functions. Then towards the end of the lecture, we introduce the moments of a distribution and introduce the concept of expected value. The last 2 points we will just revise again today, moments of a distribution and expected value, and then move on. So, if you recall, we said the nth moment about the origin. So, this is the origin and we are talking about moments of the PDF f of x, this is x. The nth moment is given by integral minus infinity to plus infinity x to the power n f of x dx. So, we are essentially taking the moment of this area about this point. The first moment, that is when n is equal to 1, the first moment about the origin, this O here represents that we are taking the moments about the origin. The first moment is called as the expected value of x, and by putting n is equal to 1 here, we get expected value of x is equal to minus infinity to plus infinity x f of x dx. So, here we have put n is equal to 1. This is also denoted by mu, and mean expected value are one and the same. So, we call it as the mean of the distribution, mean of the random variable, I am sorry. Once we define the expected value, we have fixed the expected value like this here. We start taking moments about the expected value itself, and we define the nth moment about the expected value as mu n. We do not put the O there or 0 there. So, if we write only mu n, it implies that we are taking the moments about the expected value, and that is defined as minus infinity to plus infinity x minus mu to the power n f of x dx, where f of x is the PDF of x. This will define the nth moment about the expected value. Then using these moments, we define several measures which will give the properties of the random variable. For example, how the values are distributed around the mean, what kind of central values we can expect in terms of the mean or the average value, and the maximum the value with the highest frequency, and the value that divides the distribution into two parts, and so on. So, first we define measures of central tendency, and the most important measure of central tendency is the mean, which we just defined. So, mu is given by minus infinity to plus infinity x f x dx in the case of continuous continuous random variables. In fact, this is a measure defined on the population. Then in the case of discrete random variables, or when we have a random variable taking on only discrete values with associated probability mass function, we define the mu as summation I is equal to 1 x I, which is the ith discrete random variable, into p of x I, which is the probability with which the value x I occurs, and n here is the sample size, or n is the number of values that the random variable, discrete random variable x can assume. Now, the sample estimate of the mean, remember, as I told in the last class, from the population we move on to samples which are the actual values that the random variable has taken. Our sample is actually a subset of the population, and if you have n number of values in the sample, the sample estimate of the mean is given by simply the arithmetic average, x bar is equal to x I by n, and this summation is from I is equal to 1 to n, where n is the sample size. So, this is the most important measure of central tendency, namely the mean. We also have the concepts of mode and the median. Mode is that value which occurs with the highest frequency. For example, if you have a distribution like this, that you have, let us say, a distribution something like this, and you have the highest frequency value here, this defines the mode, and median is that value which divides the distribution into two halves. That means, the area towards the right of the median is equal to area towards the left of the median, both of which are equal to 50% of the area. In most hydrologic analysis, we use the concept of the mean more often than the concepts of the mode and the median. So, it is important for us to understand the concept of mean. Then we have measures of spread or dispersion. Let us say you look at a sample consisting of values 0, 10 and 20. Let us say there are 3 values in the sample. What is the sample estimate of the mean? It will be simply the arithmetic average, and therefore, it will be 10. We have another sample which has again 3 values, but the values are 9, 10 and 11. Again the sample estimate of the mean is 10, which is the arithmetic average. Now, both of these have the same mean, but as you can see, the spread around the mean is much higher in the first case compared to the spread around the mean compared to the of the second case. And therefore, it is important for us to see how the values are spread around the mean, or how they are dispersed around the mean. And therefore, we introduce a measure for measuring the spread of the distribution around the mean. The most obvious measure is the range, which is simply given by the difference between the maximum value and the minimum value. So, it indicates actually how far are the values spread, not necessarily around the mean in this case. X max minus x min will give you the range of values that you may expect. But the more important measure of spread is the variance, which is based on the second moment about the mean, which is in fact equal to the second moment of the about the mean. So, sigma square, which is the variance, is defined as expected value of x minus mu the whole square, and recall that the expected value of a function is given by that function multiplied by the integral of that function multiplied by f of x dx. So, in this case we are looking at the expected value of x minus mu the whole square, and therefore, this is given by integral minus infinity to plus infinity x minus mu the whole square f of x dx. So, as you can expect here, for example, the spread of this distribution is much higher compared to the spread of this distribution. So, the variance that you get from this distribution is higher than will be higher than the variance from this distribution. So, the variance actually indicates how the values are spread around the mean. The higher the variance, the higher is the spread. The sample estimate for the variance, again recall that we have defined this for the population. This definition is for the population, and the sample estimate for that is given by summation I is equal to 1 to n x I minus x bar the whole square divided by n minus 1. In the case of the mean, the sample estimate was given by, you look at this point, x summation of x I over n. So, n is the sample size. Why is it that we use n minus 1 here? Of course, you can also use n as one of the estimates, but we use n minus 1 for getting what is called as an unbiased estimate of the variance. We will come to the parameter estimation subsequently in this course, but right now you remember that it is not n, but n minus 1, because we are looking at an unbiased estimate of the variance. Then we define the standard deviation as the positive square root of the variance. So, the standard deviation is simply the positive square root of variance, and the associated sample estimate for that is given by S as the positive square root of S square. Now, if you have a sample, let us say of stream flows measured in million cubic meters, then what are the units of x bar or the arithmetic average, which is a sample estimate of the mean. The x bar will also have the same units as the variable x itself. So, in this case x bar will have the units of million cubic meters. Similarly, the standard deviation, you look at this point, x I minus x bar the whole square. So, x bar has the units of the flows in this example, x I has units of flows. So, x I minus x bar the whole square has units of flow square or million cubic meter square, and when we take the square root, the standard deviation will have the same units as the original variable. So, the standard deviation in this case will have variables of million cubic meters. But when we want to compare two distributions of different random variables, let us say we want to compare the distribution of rainfall as well as the stream flows. We want to have a measure of the spread which is independent of the units, and therefore, we define what is called as coefficient of variation, and we define that as sigma over mu. As you can see, sigma has the same units as x, mu has the same units as x, and therefore, C V will not have any units, and for the sample it is given by S by x bar. So, in general we use coefficient of variation as a measure of spread when we want to have comparison with comparison among different distributions. So, we have defined sigma square as expected value of x minus mu the whole square. All these have to be capital here. Say for example, this x, because we are talking about a random variable, this is a capital random variable, sorry for that. So, this is x capital, similarly this is capital X. So, from here expected value of x minus mu the whole square, we expand this. So, we are talking about expected value of x square minus 2 x mu plus mu square. So, when we simplify this, recall the properties of the expected value. So, I can write this as expected value of x square minus 2 mu being constant, it comes out into expected value of x plus expected value of mu square. So, this will be written as expected value of x square minus 2 mu into expected value of x, which is again mu. So, this will be minus 2 mu square plus mu square. So, this will be equal to expected value of x square minus mu square, which is written as expected value of x square minus expected value of x the whole square. This is a useful result which in many situations we use, in many applications we use this particular expression. So, we defined two measures now, measures of central tendency, which will indicate how the distribution is in terms of the central values, for example, the mean, the mode, the median, etc. Then we defined a measure of the spread or the dispersion, which gives how far the values are spread from the mean. The variance is a important measure of dispersion. Now, we look at another important measure of the distribution, which gives us whether the values are symmetrically distributed or there is a skewness there, and if there is a skewness, whether it is a positive skew or a negative skew. So, we introduce a measure of symmetry, which is again based on the moments. From the first moment about the origin, which provided you the expected value of x, we went on to the second moment about the expected value, about the mean, and defined the variance, which is expected value of x minus mu the whole square, which is in fact the second moment about the expected. Like this, we keep proceeding to higher order moments. We consider the third moment about the expected value and then define a measure. Go to the higher order, fourth moment, and then define a associated measure. Like this, we keep on moving to higher order moments about the expected value. Each moment has some implication on the type of the distribution. So, as you consider higher and higher moments, you get better and better idea about the distribution itself. So, let us look at the measure of symmetry now. What is it that we are looking at? We are looking at, let us say there is a distribution something like this. There is a long tail towards the right and another distribution which has a long tail towards the left and has similar peak as any of them, and there is another distribution which is perfectly symmetrical about certain point. We define the coefficient of skewness based on the third moment. Now, whenever we are defining these measures, we normalize those measures, the associated moments with the standard deviation. What is the standard deviation? Standard deviation is mu 2 to the power half, because mu 2 is a variance, and to the power half, which is a square root, that gives you the standard deviation. So, when you take the third moment, you normalize that with the standard deviation to the power 3. When you take the fourth moment, you normalize that with standard deviation to the power 4 and so on. So, the coefficient of skewness we define here with the third moment mu 3 divided by mu 2 to the power 3 by 2. Remember, mu 2 to the power 1 by 2 is the standard deviation. So, mu 2 to the power 3 by 2 is the standard deviation cube. So, this is written as, this is your mu 3 x minus mu to the power 3 f of x dx. Recall that mu n is x minus mu to the power n f of x dx. Therefore, this term here indicates the third moment divided by sigma square, which is mu 2 to the power 3 by 2, which means sigma to the power 3. From this, we can write the expressions for the sample estimates. So, for the sample estimates, we replace the integral with the summation I is equal to 1 to n x I minus x bar. We retain the same power as the moment x minus mu the whole cube. So, we retain the same moment. Then for the standard deviation, what is it that we had? We had n to the power 0 and x I minus x bar the whole square we had here for the variance. Now, we start increasing the power in the numerator, power of n in the numerator, and start increasing the terms on the denominator. For the variance, we had n to the power 0 and here we had n minus 1. For the skewness, we put n to the power 1 and increase another term here n minus 1, n minus 2, and this s cube corresponds to the sigma cube here. So, we are essentially normalizing this term with the standard deviation same power. So, for example, if you go to the higher moment, next higher moment, you will be writing for mu 4, that is mu 4, and therefore, the denominator will be mu 4 mu 2 to the power 4 by 2, which is mu 2 square. And therefore, what we will write here? We will write for the fourth moment, we will write n square and then n minus 1, n minus 2, n minus 3, and this power becomes 4. Like this, from one moment to the next higher moment, we keep increasing the order of the moment and normalize that with respect to the standard deviation raised to the same power. Okay. The coefficient of symmetry or coefficient of skewness, as we have defined here, will indicate whether the values are symmetrically distributed or there is a negative skew, in which case the C s as defined here will be negative, or that has a positive skew, in which case the C s as defined here will have a positive value. Note that for the positive skew, the values are stretched, in the sense the distribution is stretched to the right. So, it is skewed to the right, and for the negative skew, there is a long tail to the left. So, if you have a long tail to the right, it is called as a positive skew. If you have a long tail to the left, it is called as a negative skew. Then we go to another measure called as the measure of peakedness. So, what is it that we did? First, we defined how centrally the values are distributed, then how far they are spread from the mean, and we also saw how symmetric or how skewed is the distribution of the values. So, these three gave us some idea about the distribution itself, but there is another important measure which is defined with respect to a so called normal distribution. So, if you have a normal distribution, you may have something like this. So, how peaked is the distribution? That means, you look at this distribution, for example, this is much flatter compared to the normal distribution, and then there may be another distribution which has the same spread, same mean, same mode, same median, etc., and same skewness coefficient also it may have, but it may have a different peakedness. So, the values are the distribution has a much higher peak compared to the normal, so called normal distribution. To measure this, that means how peaked is the distribution, we introduce what is called as a kurtosis. It is also called as kurtosis coefficient or coefficient of kurtosis, but in this course we will simply denote this as the kurtosis. So, as I said, we move on to higher moments from the previous one. In the previous one, we considered the third moment about the mean, we consider now the fourth moment about the mean. So, the kurtosis is defined based on the fourth moment about the mean, and then we standardize this with respect to mu 2 to the power 4 by 2. Mu 2 to the power half gives you standard deviation, and that we are raising it to the power 4. So, mu 2 to the power 4 by 2 will give you mu 2 to the power 2. So, kurtosis is given by mu 4 divided by mu 2 to the power 2, which if we write, this is again for the population, this will be minus infinity to plus infinity, and mu 4 here, which is x minus mu to the power 4 f of x dx, f of x is the PDF of x, divided by mu 2 to the power 2, which is mu 2 is sigma square, which is the variance to the power 2. The associated sample estimate is written as, recall that in the previous measure, which was measure of symmetry, we had used mu 3 there, we had n here. So, we go on to the higher power of n and write n square, and this power is the same as the power of the moment. So, x I minus x bar of to the power 4 divided by, again here we increase one term here, n minus 1, n minus 2, n minus 3, and here we have got sigma to the power 4, and therefore, we write it as s to the power 4. So, this is a sample estimate of the kurtosis. So, together these measures, namely measure of central tendency, measure of dispersion, measures of dispersion in fact, and the measure of skewness or the measure of symmetry, which is given by the coefficient of skewness, and the measure of peakedness. Together all of these will give us an idea of how the distribution is likely to be. So, if you have a sample, let us say that over the last 50 years you have observed the stream flows at a particular location. So, from this sample you should be able to estimate, you should be able to determine the sample estimates of the mean or the expected value, and the sample estimate of the variance, and therefore, the standard deviation, from which you can get the coefficient of variation, and also estimate the coefficient of skewness or the coefficient of symmetry, and the coefficient of kurtosis, or in this particular case we call it as kurtosis, simply call it as kurtosis. So, these measures will give us, as I said, an idea about which type of distribution this sample may fit. Let us take an example, numerical example. First, we will work with the expected value alone. Let us say you have a PDF f of x is equal to 3 x square, and which is defined for x varying between 0 and 1. Let us obtain the expected value of x and the expected value of a function defined on x, which is 3 x minus 2, and the expected value of x square, which is another function defined on x. So, the expected value of x is simply given by minus infinity to plus infinity x f of x dx, and because f of x is defined to be non-zero between the range 0 and 1, we integrate between 0 and 1. This is x, this is f of x 3 x square with respect to x. So, we get it as 3 by 4. So, the expected value of x is 3 by 4. This is also mean, and it is also denoted by mu. Then the expected value of any function of x is given by integral minus infinity to plus infinity that particular function into f of x dx. So, expected value of 3 x minus 2 is given by minus infinity to plus infinity 3 x minus 2 into f of x, which is 3 x square into dx, and when you integrate that you will get 1 by 4. Similarly, the expected value of x square is given by minus infinity to plus infinity x square f of x dx. This is the function, x square is the function, and this is PDF, and this you will get it as 3 by 5. Recall that expected value of x square can be used to get the variance once you have expected value of x. We wrote expected value, that is sigma square. For example, sigma square we wrote it as expected value of x square minus expected value of x the whole square. So, we can get the variance from expected value of x and expected value of x square. We will take another example where we have a sample. The previous example consisted of population estimates. For example, this is the expected value based on the PDF defined for the population. Now, we will go to an example where we have a sample of values. For example, average yearly stream flow at a particular location. So, these have been measured for last 15 years. Although, I must alert you that when you are using the sample estimates and then using these sample estimates for the population as approximation for the population measures, we must have larger number of values here, larger number of years of observation, not just the 15 years, but as an example we will take 15 years now. So, these are the observed values 150, 129 and so on. So, these are given for the last 15 years. So, when you have observed values and you want to have an idea of the distribution, you use the sample estimates for the measures that we just defined, namely the x bar, which is a estimate for the mean, S square, which is the estimate for the variance sigma square, and the coefficient of skewness, which is denoted as CS for the sample estimates, and the kurtosis, which is K. So, first we get the sample estimate for the mean as simply the arithmetic average x bar by n, simply add up all the values divided by the number of values, which is 15 in this case. So, you get the sample mean as 135 million cubic meters, and the variance is given by x I minus x bar the whole square by n minus 1. So, the once you get the sample mean or the x bar, you open out a tabular column, because you need all these powers x I minus x bar the whole square, x I minus x bar the whole cube and so on. You need all these columns. So, we will open out a tabular column like this. So, this column gives you the year number and then these are the values. So, these are actual x I values. So, this is I is equal to 1, I is equal to 2 etcetera, goes on up to I is equal to 15, and these are the x I values, x 1 is equal to 150, x 2 is equal to 129 and so on. So, sum it over, you get 2025, and 2025 by 15 gives you the mean, which was 135 as obtained before. So, this is your arithmetic mean. So, we use this 135 and then get x I minus x bar which is 150 minus 135, which is 15. Remember that because x bar can be greater than x I, you can have negative values here, there will be some negative values. In fact, a first order check of whether you are doing your computations right is that the summation of the first order deficit deviation, which is x I minus x bar, must be equal to 0. Then we get x I minus x bar the whole square, which is simply this term square minus 6 square, 25 square and so on. Now, this you add it up to you get the variance. So, how do we get variance? This is summation of x I minus x bar the whole square divided by n minus 1. So, this is summation of x I minus x bar the whole square divided by n minus 1, which is 15 minus 1, 14. That is how you get the variance. Similarly, we go to coefficient of skewness, you add up x I minus x bar the whole cube, because the order of the power is odd, you will get negative values here. So, there will be also negative values, not only the negative values, and then you sum it over and then divide it by you use your sample estimate formula to get the coefficient of skewness. Then you go to x I minus x bar the whole cube, which is whole to the power 4, which is these values raised to the power 4, sum them over, you get the fourth order power of the deviation x I minus x bar. Use these to get the sample estimates. For example, sample estimate for the variance is sigma x I minus x bar the whole square. So, this is what I have written here is sigma x I minus x bar the whole square divided by n minus 1. This is I is equal to 1 to n. Similarly, then you take the standard deviation, which is the positive square root of the variance, you get 23.8 million cubic meters. Then we get the coefficient of variation, which is s by x bar. Recall that we define the coefficient of variation to obtain a unitless measure of the spread or the deviation. So, you get S by x bar as 0.176. Then coefficient of skewness, we use the third power of the deviation x I minus x bar the whole cube divided by n minus 1 n minus 2 s to the power 3. You have got s here and then that s you use here, and this minus 29916 is obtained from the summation of this term here x I minus x cube. So, this is minus 29916. We use that and then the standard deviation to the power 3. So, we get the C s as minus 0.183. Remember that the coefficient of skewness can be negative. So, when it is negative, we get a negatively skewed distribution. Then we get also the coefficient of kurtosis, which is also called as simply kurtosis, k is equal to n square, which is 15 square, and x I minus x bar the whole to the power 4. In this case, it was 6678008, which is the summation of this column here, and you use that, raise the standard deviation to the power 4. You have n minus 1, n minus 2, n minus 3, which is 14, 13 and 12, then you get 2.14. If the kurtosis is less than 3, then it is called as platykurtic, and it generally indicates a flat distribution. For example, a platykurtic distribution will have some shape something like this. If this was your normal distribution, this would be k is equal to 3. Recall that we defined the normal distribution like that. If k is less than 3, you may expect a flat distribution like this. So, the lower the k, the flatter will be the distribution. So, in this particular case, you get 2.14 as the kurtosis, which is less than 3, and therefore, it is a platykurtic distribution. So, what is it that we did so far? That if we have a sample of observed values, we first get an idea of what kind of distribution we may expect this particular sample to follow. This we did with several measures, measures of central tendency, measure of soft spread, how far are the values spread from the mean, and then how symmetric is the distribution, is there a symmetry in the distribution or there is a lack of symmetry, if there is a skewness, whether it is positively skewed or negatively skewed, then how peaked are the is the distribution with respect to some normally defined distribution and so on. So, this gives from the sample of values that we have, we get a idea of what kind of distribution we may expect for the sample to follow. Now, from several applications, there are a large number of distributions which have been defined for hydrologic applications, also for other applications. Recall that when we introduced the concept of PDF, probability density function, we said any function that satisfies those conditions. For example, f x must be non-negative, f x is greater than or equal to 0, and the integral minus infinity to plus infinity f of x dx must be equal to 1. So, any function that satisfies these two conditions is a potential candidate for being a PDF in the continuous case, that is a continuous random variable. So, there are a handful of distributions which are commonly used in hydrology. We will see some of them. The idea here is that if we want to use, let us say you have data for the last 20 years of stream flow, and you have estimated all these different measures. So, for example, x bar you have estimated, s square you have estimated, coefficient of skewness you have estimated, coefficient of peakedness you have estimated. From these, you would like to use a well defined distribution. So, we will go through some of the distributions that are commonly used in hydrology, and we will also see some applications where a particular type of distribution is used for a particular type of process. For example, if you have daily rainfall, what kind of distributions are normally used, and monthly stream flows or seasonal flows when the time scales are large and the processes are more or less normal processes, what kind of distributions we use and so on. So, we will introduce some distributions today and maybe continue on to the next class also. These distributions are commonly used for several hydrologic applications. The most commonly used distribution is the normal distribution. In fact, the normal distribution in hydrology, we use it for most so called normal processes. For example, monthly stream flows, seasonal rainfall, the smoothened processes, which are aggregates over large amount of time. And the normal distribution is also called as the bell shaped distribution, and after the German mathematician who introduced this distribution, it is also called as the Gaussian distribution. In fact, the normal distribution was first introduced for analysis of errors from the observed data and the simulated or the experimental data. So, we use the normal distribution, as I said, in most cases where we have aggregation of values over some smoothened process. For example, if you are talking about monthly stream flows, seasonal rainfall or seasonal evapotranspiration, where the values can be considered as summation of smaller processes, large number of smaller processes, we can use normal distribution as a first cut approximation. The normal distribution is also the most commonly used distribution in many of the hydrologic applications. Many of the hydrologic applications where we are dealing with normal processes, again I repeat. For example, you are looking at the inflows to a reservoir or the storage levels in the reservoir, which are operated based on a certain operating policy. So, how the reservoir levels are fluctuating. Now, such normalized processes which are an aggregate of smaller processes happening over a fairly reasonably large amount of time, we can approximate them using normal distribution. Now, the normal distribution has very interesting properties, because of which it becomes the most commonly used distribution. First, it is a perfectly symmetrical distribution, and it is symmetrical about the mean mu of the random variable x. The PDF f of x for the normal distribution is given by 1 over root 2 pi sigma exponential of minus 1 by 2 x minus mu by sigma the whole square, and this is defined for minus x varying between minus infinity to plus infinity. As you can see from the distribution, this is the PDF. It has two parameters, mu and sigma. So, once you define parameters mu and sigma, this PDF is completely defined. So, it is called as it has two parameters mu and sigma, and we denote it by x follows normal distribution with two parameters mu and sigma square. We use this notation. So, when we use this notation, it means that x is a random variable which follows the normal distribution with parameters mu and sigma square. Sigma square is the variance. So, many times you may see that the notation consists of n mu sigma. It does not matter, it only indicates that instead of variance you are using the standard deviation. The distribution approaches 0 asymptotically as x goes to minus infinity or plus infinity, and it is symmetric about x is equal to mu. The mean, the mode and the median are all the same. So, x is equal to mu also defines the mean and the median and the mode, because this is also the highest frequency value. Then there are other interesting properties of normal distribution. because it is perfectly symmetrical, you have a gamma s which is a coefficient of skewness to be 0. Recall that if it is a symmetric distribution, you get gamma s as 0. So, normal distribution has a coefficient of skewness of 0, and kurtosis is actually defined with respect to normal distribution. So, kurtosis of gamma normal distribution is 3. But a useful result of the normal distribution is that if x is a normal distribution, normally distributed with mu and sigma, that is we are talking about x here as normally distributed with mu and sigma square, and we define a linear function on x, y is a linear function on x, then y is also normally distributed. So, y we define as a plus b x, which is a linear function of x, then y is also normally distributed. It can be shown very easily that y is also normally distributed with the parameters a plus b mu and b square sigma square. That means, the mean of the random variable y will be a plus b mu and the variance of the random variable y will be b square sigma square. Then now we look at the CDF of x. So, f of x is given by minus infinity to plus infinity, minus infinity to x, I am sorry, minus infinity to x. This is the CDF we are talking about, f of x dx, which will be 1 by root 2 pi into sigma minus infinity to x e to the power minus half x minus mu by sigma the whole square dx, and this is for x varying between minus infinity to plus infinity. Now, if you have a sample and you have estimated the you have obtained the sample estimates for mu and sigma, then you should be able to get the f of x, because your small f of x is completely defined in that case, and therefore, you should be able to get f of x, if you are able to integrate this between minus infinity to x. Also, as your mu and sigma change for different samples, your PDF itself changes, because it is a 2 parameter PDF. Therefore, as the parameter values change, your PDF changes, and therefore, you need to obtain this integral for a specified values of mu and sigma. Because this integration is not easily possible, we adopt numerical integration, and when you want to do numerical integration, if you have to do it for every given mu and sigma, then it becomes cumbersome. So, we use this important result, that if we define a function on the random variable x, a linear function on random variable x, then we know that y also follows normal distribution with parameters specified like this. So, we should be able to transform the random variable x as a linear function of, I am sorry, I will repeat that. If you have the random variable x, you should be able to obtain a linear transform of x, which also follows the normal distribution with parameters a plus b mu and b square sigma square. We use this result and generalize the integration for the normal distribution. So, look at this transformation, z is equal to x minus mu over sigma. This is a linear function, and in our earlier notation, from our earlier notation where we wrote y is equal to a plus b x, if we use that, here a will be minus mu over sigma, this part, and b is 1 over sigma from here. So, because y follows in this particular case a normal distribution with a plus b mu and b square sigma square, this is the mean of random variable y, and this is the variance of the random variable y. So, substituting this here, z should follow normal distribution with a plus b mu. So, this is a plus b mu. So, you get this as 0 and 1 b square sigma square as a variance. So, you get the parameters of the normal distribution that z follows as 0 and 1, and this becomes a extremely handy result, because once we have this transformation z is equal to x minus mu over sigma, z follows a normal distribution with 0 mean and unit variance, and therefore, we should be able to define the CDF of z and use the integration to obtain the associated probabilities on x. So, once we define z, we define the PDF of z. Because z follows normal distribution, we obtain the PDF of z as 1 over root 2 pi, sigma is 1, therefore, we do not write sigma here, e to the power minus z minus mu z the whole square was there, and mu is 0 here for this, therefore, you get e to the power minus z square by 2, and z varies between minus infinity to plus infinity, because x varies between minus infinity to plus infinity. So, once we get the PDF of z, you get the CDF of z as integration between minus infinity to z 1 over root 2 pi, that is this f of z, and you get this integral here minus infinity to z e to the power minus z square by 2 dz. Recall that your CDF of z, what does it give? It gives you, that is, you are talking about f of z, this gives you probability that z is less than or equal to z. So, for a specified value of z, we should be able to get the probability of z is less z being less than or equal to that value, if we can integrate this function e to the power minus z square by 2 with respect to z. However, again the integration of this is not easily possible with our usual routine methods, and therefore, we have to go for numerical integration. But the advantage here is that because it has a 0 mean and unit variance, it does not have any parameters, and therefore, for a specified value of z, you can integrate this and then give the integral values, that is probability of z being less than or equal to z for various values of z, and that is what is done using the numerical integration. So, what is it that we did? Starting with the normal distribution, we obtained a transformation on the random variable x. We defined z, which is now called as the standard normal deviate or standard normal variable. So, from x we obtain a transformation z is equal to x minus mu over sigma, and then see that z follows a normal distribution with mean as 0 and standard deviation as 1. Let us look at how the standard normal distribution looks like. So, the f z, which is the PDF of z, is referred as standard normal density function. So, if you plot the standard normal density function, it looks like this. It is perfectly symmetrical about x is equal to about z is equal to 0. Then another interesting property here is that if you take one standard deviation on either side, the standard deviation of z is 1. Therefore, if you take one standard deviation here and one standard deviation here, the area contained within that is about 68%. About 68% of the PDF is contained in one standard deviation around the mean, which is 0. And you take two standard deviations, that is between minus z is equal to minus 2 to z is equal to plus 2, about 95% of area is contained in that. So, this area between z is equal to minus 2 to z is equal to plus 2 contains 95% of the area. And similarly, 3 standard deviations if you take minus 3 to plus 3, that is z is equal to minus 3 to plus 3, about 99% of the area of under this PDF is contained within this region. Now, this has an important connotation or implication, that when you are dealing with some normal processes, not really the extreme processes like this. That is, you are not concerned about what is happening to the tail of the distribution or on the extreme right of this distribution. About 99% of the values lie within plus or minus 3 standard deviations. Now, because as I said f z cannot be integrated analytically by ordinary means, we use numerical integrations and then tabulate them for various values of z. We tabulate the area under the standard normal curve or the standard normal density function, and then given a value of x for which we are interested in obtaining the probabilities. Let us say that probability of x being less than or equal to a given value of x you are interested in. You use the transformation z is equal to x minus mu over sigma, and then start talking about the probabilities on z rather than probabilities on x using the tables that we generate using numerical integration. So, with this now we will pause for today and we will continue the discussion in the next class. So, what is it that we did today? We started with the definitions of the moments. We take the moments about the origin, define the moments about the origin first. So, the first moment about the origin we call it as the expected value, and then once we define the expected value, we start taking moments about the expected value and define the higher order moments about the expected value itself. We introduced measures of central tendency as the mean or the expected value itself, and the mode and the median. Then we went on to see the measure of dispersion, which is the variance, which we defined as the second moment about the mean. And then we also introduce measures of symmetry, which is based on the third moment about the mean, and we also obtained the associated sample estimates. Then we looked at the measures of peakedness, which is the kurtosis, and kurtosis is defined based on the fourth moment about the mean. Then we looked at the most commonly used distribution, which is the normal distribution. We saw that the normal distribution is perfectly symmetrical, and therefore, the coefficient of skewness is 0 and the kurtosis is 3, and then normal distribution has important property that a linear function defined on the random variable following a normal distribution also follows normal distribution, and we use this result, this important result, to obtain what is called as the standard normal density function. And we defined the CDF of the standard normal density function or standard normal variable, and we now move on to tabulating the CDF values for the standard normal variable. So, we will continue the discussion in the next class, and we will solve some examples using the normal distribution, and we will acquaint ourselves with the use of the standard normal tables. Thank you very much for your attention.